So this is part two of the introduction, and here we're going to do a little bit of the discussion of sort of the way certain physical quantities are treated differently from other physical quantities. We divide physical quantities mathematically into two groups, at least for the purposes of this class. One group is called scalars and one group is called vectors. And that's what this PowerPoint is about. So a scalar physical quantity has just a value. Examples of scalar physical quantities are temperature, or mass, or length, or speed, or area, or volume, or energy. These have only a value or a magnitude. We use the words value and magnitude a lot when we're talking about the number in units associated with something. So 10 meters per second is a magnitude. 15 pounds is a magnitude. Scalar physical quantities do not have an associated direction with them. If I say it's 40 degrees outside, or a bottle has 1 liter of water, there's no direction associated with those physical quantities. The mass of an insect is 7 grams. The diameter of a basketball is 9.55 inches. Those are all scalars. They don't need to be represented including a direction, and so they're called scalars. A vector physical quantity has both a value, or magnitude, and a direction. Some vector physical quantities are velocity, displacement, acceleration, force, momentum. So here are a few examples of those. A hawk's velocity is 30 miles per hour due north. So the magnitude is the 30 miles per hour, and the direction is due north. I can say I traveled 7 miles in a direction 20 degrees south of west. That would be a displacement, right? I traveled 7 miles, that's how far I traveled, that's the distance or the length. And then the direction is 20 degrees south of west. That makes it a displacement. A displacement is a vector version of a length. It includes the direction. Anytime you're including the direction in something, you're making a vector out of it. Many physical quantities naturally have vectors associated, naturally are vectors. While pumping his basketball, Bob exerted a 30-pound downward force on the pump's handle, right? The magnitude of the force is 30 pounds. The direction is downward. The rocket accelerated 200 meters per second squared straight up, right? Once again, a magnitude and a direction, that's a vector. Generally, we represent vectors by arrows, with the length of the arrow representing the magnitude of the physical quantity, and the direction the arrow is pointing indicating the direction of the vector. So just here are a few examples. I have two velocity vectors. One is 25 meters per second, and it points 30 degrees, say, north of east. If north is straight up the page, say. In the same figure, that could be a bird flying or something like that. I could have another vector that's 10 meters per second and pointing west, right? Notice this guy is sort of pointing at least potentially in the direction 30 degrees north of east if north is straight up the page. And in that context, this one is pointing west. West is to the left across the page if east is to the right, right? Also notice that this vector is proportionally shorter because it's representing 10 meters per second, whereas this vector up here is representing 25 meters per second. You can also, it doesn't just have to be velocities. Here's a force that's 10 newtons down. Now, these two are in different contexts, right? This force is down and over by the velocities would be south because I was using north, south, east, and west. But as long as you pick your coordinate system and are consistent with it throughout your example, that's all fine. So here, I'm just going to give you a few examples of these. Traveling by foot or helicopter, right? Velocity, vector displacements can be added. And so I go 5 blocks north and then 9 blocks east, and I end up over here, right? Or I can go 9 blocks east and then 5 blocks north, and I still end up here, right? And so, or I could just fly 10.3 kilometers along the hypotenuse, as we say, and if you took 9 squared, if you use the Pythagorean theorem, if you remember that one, 9 squared plus 5 squared and took the square root, you get 10.3. And so these two vectors, the north one and the east one, add up to the diagonal vector. So here's some other force examples when we start talking about um, forces acting on objects. There, we can look at the forces acting on the swimmer, or the swimmer's exerting on the wall. When a swimmer pushes against a wall, there's an equal and opposite force pushing out on the swimmer, and that's, so you see a force due to the feet on the wall, or force due to a wall on the feet. We'll talk about that more when we get into Newton's laws. But if you notice, the swimmer is not moving up or down vertically, right? Swimmers are just swimming along horizontally, mostly in the water. But there are two forces. There's the weight of the swimmer, and then there's a buoyant force due to the water. And so we have an upward buoyant force and a downward weight force that cancel each other out. You can sort of see they've got about the same size, and they're pointing in opposite directions. But then there's a wall force on the swimmer that pushes the swimmer to the left in the picture. So this is called a free body diagram. It's just a vector diagram. We can see how forces add. Here are two ice skaters. One ice skater is exerting F1 on the middle skater, and the other one is exerting F2. And so the skater is going to follow the sum of those two vectors. If you put them tip to tail, and then draw a line from the beginning of the first one to the tip of the second one, you get the net effect. If these two skaters push on this skater as they're drawn, this skater will go off in this direction. And so here's some questions. What are the two basic components of a vector? We talked about that. List three physical quantities that are vectors. This one should say list three physical quantities that are scalars. Someone says that a car's velocity is 25 meters per second. What did they omit there? And finally, a force of 100 newtons acts to the right on a block, while a force of 150 newtons acts to the left on the same block. What's the net force acting on the block? What's the net effect of 100 newton force to the right and 150 newton force to the left?